Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Here we will learn about different concepts related to civil engineering. Time to enter the world of civil engineering. In today's video we are going to discuss about hydraulic machines pumps. Hydraulic machines are basically defined as those machines which convert either hydraulic energy into mechanical energy, which will be further converted into electrical energy, or mechanical energy into hydraulic energy. Pumps. Pump is a device which is used to convert mechanical energy into hydraulic energy. Here hydraulic energy refers to potential and kinetic energy of a liquid. Hydraulic pumps are the energy-absorbing machines. Since it requires mechanical power to run, it is mainly of two types: centrifugal pump, reciprocating pump. Centrifugal pump. The hydraulic energy is in the form of pressure energy. If the mechanical energy is converted into pressure energy by means of centrifugal force acting on the fluid, the hydraulic machine is called centrifugal pump. The centrifugal pump acts as a reverse of an inward radial flow reaction turbine. This means that the flow in centrifugal pump is in the radial outward directions. The centrifugal pump work on the principle of forced vortex flow. That means when a certain mass of liquid is rotated by an external torque, the rise in pressure head of rotating liquid takes place. The rise in the pressure head at any point outlet of the impeller is proportional to the square of the tangential velocity of the liquid at that point. Rise in pressure head equals V2/2G or omega-2R 2 grams. Hence at the outlet of the impeller where the radius is more, the rise in pressure head will be more and the liquid will be discharged at the outlet with a high pressure head. Due to this high pressure head, the liquid can be lifted to a higher level. A centrifugal pump is also known as a rotodynamic pump or dynamic pressure pump. Generally, centrifugal pumps are made of the radial flow type only. But there are also axial flow or propeller pumps which are particularly adopted for low heads. These are the most popular and commonly used type of pumps for the transfer of fluids from low level to high level. It is used in places like agriculture, municipal, water and wastewater plants, industrial, power generation plants, petroleum, mining, chemical, pharmaceutical and many others. Centrifugal pumps can be used for viscous and non-viscous liquids and has higher efficiency. Main parts of centrifugal pump. The main parts of centrifugal pump are: impeller, casing, suction pipe with a foot valve and astra inner, delivery pipe, delivery valve, impeller. Centrifugal pump impeller is the main rotating part of the machine. It consists of a series of backward curved vanes. It is placed on a shaft which is straightly connected to the shape of an electric motor. It is a wheel or rotor which is provided with a series of backward curved blades or vanes. It is mounted on the shaft, which is coupled to an external source of energy which imparts the liquid energy to the impeller, thereby making it to rotate. Different types of impeller are discussed below in classification section. Casing: it is a pipe which is connected at the upper end to the inlet of the pump to the center of impeller, which is commonly known as eye. The double-end reaction pump consists of two suction pipe connected to the eye from both sides. The lower end dips into liquid into lift. The lower end is fitted into foot valve and strainer. Casing is an airtight chamber surrounding the impeller. The shape of the casing is designed in such a way that the kinetic energy of the impeller is gradually changed to potential energy. This is achieved by gradually increasing the area of cross-section in the direction of flow. The design of the casing of centrifugal pump is almost similar to the casing of air-reaction turbine. Following three types of casing are commonly used of a centrifugal pump. Volute casing, Vortex casing, casing with guide blades. Volute casing. Volute casing is aspiral type casing which surrounds the impeller. It increases the area of flow gradually. Increase the area of the flow decreases the velocity of flow as well as increases the pressure of the water flowing through the casing. Volute casing increases the efficiency of the pump, but a large amount of energy is lost due to formation of eddies. Vortex casing. Vortex casing is a circular chamber placed in between the casing of the pump and the impeller as shown in figure. Formation of eddies is reduced for the circular chamber and the loss of energy is reduced to a considerable amount. Efficiency of a pump in vortex casing is much higher than the efficiency of volute casing. Casing with guide blades. This type of casing, the impeller is surrounded by a series of guide blades mounted on airing which is known as diffuser. The guide vanes are designed in such a way that the water from the impeller enters the guide vanes without stock. Increase the area of guide vanes, reducing the velocity of flow through guide vanes and also increasing the pressure of water. Now the water from the guide vanes passes through the surrounding casing which is connected with the impeller. Suction pipe with a foot valve and a strainer. Suction pipe of centrifugal pumps. One end is connected to the inlet of the pump and other end dips into water in a sump. Foot valve is a one-way type valve that is fitted at the lower end of the suction pipe. It is open only the upward direction. Strainer is also fitted at the lower end of the suction pipe. Suction pipe is connected with the inlet of the impeller and the other end is dipped into the sump of water. At the water end, it consists of foot valve and strainer. The foot valve is a one-way valve that opens in the upward direction. The strainer is used to filter the unwanted particle present in the water to prevent the centrifugal pump from blockage. Delivery pipe. It is a pipe whose one end is connected to the outlet of the pump and another end delivers the water at a required height is known as a delivery pipe. It is a pipe which is connected at its lower end to the outlet of the pump, and it delivers the liquid to the required height. Near the outlet of the pump on the delivery pipe, a valve is provided which controls the flow from the pump into delivery pipe. Delivery valve. Delivery valve is a valve which can regulate the flow of liquid from the pump. Different types of centrifugal pump. According to the construction, application, design, and service, there are 3 types of centrifugal pump are available. 1. According to the shape of impeller and casing. 2. According to the type of impeller. 3. According to the working head. These 3 types of centrifugal pumps are also divided into sub-3 categories. According to the shape of impeller and casing. Volute or spiral casing type pump. Vortex, whirlpool, casing type pump. Diffuser type pump. According to the type of impeller. Closed or shrouded impeller. Semi-open impeller. Open impeller. According to working head. Low head centrifugal pump. Medium head centrifugal pump. High head centrifugal pump. According to the shape of impeller and casing. In the case of a volute pump, a spiral casing is provided around the impeller. The water which leaves the vanes is directed to flow in the volute chamber circumferentially. The area of the volute chamber gradually increases in the direction flow. Thereby the velocity reduces and hence the pressure increases. As the water reaches the delivery pipe, a considerable part of kinetic energy is converted into pressure energy. However, the eddies are not completely avoided, therefore some loss of energy takes place due to the continually increasing quantity of water through the volute chamber. In the case of a diffuser pump, the guide wheel containing a series of guide vanes or diffuser is the additional component. The diffuser blades, which provides gradually enlarging passages, surround the impeller periphery. They serve to augment the process of pressure build-up that is normally achieved in the volute casing. Diffuser pumps are also called turbine multistage pumps, and vertical shaft deep well pumps fall under this category. According to the type of impeller. Impellers are divided into 3 types. Open impeller. An open impeller has vanes that are attached to a center hub and mounted directly onto a shaft. There is no wall surrounding the vanes, which makes open impellers weaker than closed or semi-closed valves. Open impellers are generally faster and easier to clean and repair. Open impellers are usually used in smaller pumps and pumps that handle suspended solids. Semi-enclosed impeller. Enclosed impeller. Closed impellers have a back and front wall around the vanes, to increase strength. Closed impellers are used primarily in larger pumps and can be used in applications that handle suspended solid service. These types of impellers are commonly found in clear liquid applications. They don't do well with solids and are difficult to clean if they become clogged. Semi-closed impellers have a back wall that adds strength to the impeller. Semi-closed impellers are usually used with liquids or products that have solids. Reduced efficiency is a common problem with semi-closed impellers, but the ability to pass solids is an important trade-off. Classification according to the working head. Centrifugal pumps may be classified into low, medium, and high head pumps. Low-head centrifugal pumps. These are usually single-stage centrifugal pumps and work below 15 mHead. Medium-head centrifugal pumps. When the head lies between 15 and 45 m, the pumps are called medium-head centrifugal pumps. High-head centrifugal pumps. When the head exceeds 45 m, the pumps are known as high-head centrifugal pumps. Usually these are multi-stage pumps, and are provided with guide vanes. These pumps may have horizontal or vertical shafts. Vertical shafts are useful in deep wells. Work done by the centrifugal pump on water. In case of centrifugal pump, work will be done by the impeller on the water. Expression for the work done by the impeller on the water will be determined by drawing the velocity triangles at inlet and outlet of the impeller. Let us see here a typical section of a centrifugal pump that indicates the impeller blade as displayed here in following figure. We are interested here to find out the work done by the centrifugal pump on the water. Energy interaction will take place only in the rotor, i.e. impeller of the centrifugal pump. Velocity triangles will be drawn at the inlet and outlet tips of the vanes fixed to an impeller. For best efficiency of the pump, water need to enter the impeller radially at inlet. Therefore, absolute velocity of water at inlet will make an angle of 90 degrees with the direction of motion of the impeller at inlet. As we have discussed above, that absolute velocity of water at inlet will make an angle of 90 degrees with the direction of motion of the impeller at inlet. Therefore angle alpha equals 0 and velocity of whirl at inlet v W1 equals 0. Let us assume the following data as mentioned here. N equals speed of the impeller in RPM d. 1 equals diameter of the impeller at inlet U. 1 equals tangential velocity of impeller at inlet V. 1 equals absolute velocity of water at inlet V. R1 equals relative velocity of water at inlet. Alpha equals angle made by absolute velocity of water at inlet with the direction of motion of vane. Theta equals angle made by relative velocity of water at inlet with the direction of motion of vane. D 2 equals diameter of the impeller at outlet U. 2 equals tangential velocity of impeller at outlet V. 2 equals absolute velocity of water at outlet V. R2 equals relative velocity of water at outlet. Beta equals angle made by absolute velocity of water at outlet with the direction of motion of vane. Phi equals angle made by relative velocity of water at outlet with the direction of motion of vane. Tangential velocity of water at inlet, U 1 equals pi d 1 n/60 tangential velocity of water at outlet, U 2 equals pi d 2 n/60. As we know that in case of radially inward flow reaction turbine, the work done by the water on the runner per second per unit weight of the water striking per second will be given by following equation as mentioned here. Work done by the water on the runner per second per unit weight of the water striking per second equals 1/g xv W1 U 1 V W2 U 2. As we know that a centrifugal pump is the reverse of a radially inward flow reaction turbine, therefore work done by the impeller on the water in case of a centrifugal pump will be given by following equation as mentioned here. Work done by the impeller on the water per second per unit weight of the water striking per second equals work done in case of turbine. Work done by the impeller on the water per second per unit weight of the water striking per second equals 1/g xv W2 U 2 V W1 U 1. Work done by the impeller on the water per second per unit weight of the water striking per second equals 1/g xv W2 U 2. Because absolute velocity of water at inlet will make an angle of 90 degrees with the direction of motion of the impeller at inlet, therefore angle alpha equals 0 and V W1 equals 0. Above equation also provides the head imparted to the water by the impeller or energy given by impeller to the water per unit weight per second. Work done by the impeller on water per second equals W/g xv W2 U 2, where W equals weight of water. W equals rho xg xq, where Q equals flow rate of water. Q equals area x velocity of flow. Q equals pi xd 1 xb 1 xv f1 equals pi xd 2 xb 2 xv f2 where B 1 and B 2 are the width of impeller and V F1 and V F2 are the velocities of flow at the inlet and outlet. Therefore, we have seen here two very important terms, i.e. work done by the centrifugal pump on water and head imparted to the water by the impeller, or energy given by impeller to the water per unit weight per second. Work done by the impeller on water per second equals W/G, 15. W2 U 2 Head imparted to the water by the impeller, or energy given by impeller to the water per unit weight per second equals 1/G, 15. W2 U 2 Heads and efficiencies of a centrifugal pump. Here we will see here the various types of heads, and after that we will see efficiencies of a centrifugal pump. Suction head, H S. Suction head is basically defined as the vertical distance between the center line of centrifugal pump and the free surface of liquid, e.g. water, in the tank from which liquid is to be lifted. This vertical distance is also termed as suction lift. The tank from which liquid need to be lifted will be termed as sump. Suction head or suction lift will be displayed by the symbol H S, as displayed here in figure. It is expressed as meters. Delivery head, H D. Delivery head is basically defined as the vertical distance between the center line of centrifugal pump and the free surface of water in the tank to which water need to be delivered. Delivery head will be displayed by the symbol H D, as displayed here in figure. It is expressed in meters. Static head, H S. Static head is basically defined as the sum of suction head and delivery head, and it will be displayed by the symbol H S. Mathematically, we will write the expression for static head as mentioned here. H S equals H S plus H D. It is expressed as meters. Manometric head, H M. The manometric head is basically defined as the head against which a centrifugal pump has to do the work. Manometric head will be displayed by H M. Let us see here the expression for manometric head as mentioned here. Manometric head equals head imparted by the impeller to the water loss of head inside the pump. Manometric head equals V W2 U 2 /G loss of head inside the pump. If there is no loss of head inside the pump, we will have following expression for manometric head as mentioned here. Manometric head equals V W2 U 2 / G, where V W2 equals velocity of whirl at outlet U 2 equals tangential velocity of impeller at outlet G equals acceleration due to gravity. Manometric head could be expressed by the following expression also as mentioned here. Manometric head equals total head at outlet of the pump, total head at the inlet of pump. Equals P O rho G plus V O 2/2 grams plus Z O P I rho G plus V I 2/2 grams plus Z I, where P O rho G equals pressure head at the outlet of the pump, i.e. HDV O 2/2G equals velocity head at the outlet of the pump, i.e. V D 2/2 grams Z O equals vertical height of the outlet of the centrifugal pump from datum line, i.e. Z D P I rho G equals pressure head at the inlet of the pump, i.e. HSV I 2/2G equals velocity head at the inlet of the pump, i.e. V S 2/2 grams Z I equals vertical height of the inlet of the centrifugal pump from datum line, i.e. Z S. Manometric head could be expressed by the following expression also as mentioned here. Manometric head equals suction head plus delivery head plus frictional head loss in suction pipe plus frictional head loss in discharge pipe and velocity head in delivery or discharge pipe. Manometric head equals H S plus H D plus H Fs plus H Fd plus V D 2/2 grams, where H S suction head H D delivery head H Fs frictional head loss in suction pipe H Fd frictional head loss in delivery pipe V D 2/2 grams velocity of water in delivery pipe. Efficiencies of a centrifugal pump. Let us first understand that how power will be transmitted from electrical motor to centrifugal pump. Power will be transmitted from electrical motor shaft to shaft of the centrifugal pump. Further power will be transferred from shaft of the centrifugal pump to impeller of the centrifugal pump. Further, power will be transferred from pump impeller to the water. Therefore, if we think the power transmission here, we will easily conclude that there will be some losses of power when power will be transmitted between pump shaft to pump impeller and further between pump impeller to the water. There will be following efficiencies related with centrifugal pump that we will discuss here. Manometric efficiency, eta. Man. Mechanical efficiency, eta. M. Overall efficiency, eta. O. Manometric efficiency, eta. Man. Manometric head is basically defined as the ratio of manometric head to the head imparted by centrifugal pump impeller to the water. Mathematically, manometric efficiency will be written by the following equation as mentioned here. Manometric efficiency, eta. Man. Equals manometric head imparted by centrifugal pump impeller to the water. The power at the impeller of the pump will be more than the power given to the water at outlet of the pump. Manometric efficiency will also be defined as the power given to the water at outlet of the pump to the power available at the impeller of the pump. Manometric efficiency, eta. Man. Equals power given to the water at outlet of the pump, power available at the impeller of the pump. Eta. Man. Equals G times H. M. V. W2. U. 2. Mechanical efficiency power at the shaft of the centrifugal pump will be more than the power available at the pump impeller. Mechanical efficiency will be defined as the ratio of power available at the pump impeller to the power available at the shaft of the centrifugal pump. Mechanical efficiency, eta. Mech. Equals power available at the impeller of the pump / power available at the shaft of the centrifugal pump. Eta. Mech. Equals Wg times V. W2. U. 2. 1000 shaft power. Overall efficiency, eta. O. Overall efficiency will be defined as the ratio of power output of the pump to the power input to the pump. Power output of the pump in kilowatt equals weight of water lifted, W, times H. M. 1000 power input to the pump equals power supplied by the electric motor equals shaft power of the pump. Eta. O. Equals W times H. M. 1000 shaft power. Eta. O. Equals eta. M. Times eta. Mech. Working of centrifugal pump. The first step in the operation of a centrifugal pump is priming. Priming is the operation in which suction pipe casing of the pump and the position of fluid with the liquid which is to be pumped so that all the air from the position of pump is driven out and no air is left. The necessity of priming of a centrifugal pump is due to the fact that the pressure generated at the centrifugal pump impeller is directly proportional to density of fluid that is in contact with it. After the pump is primed, the delivery valve is still kept closed and electric motor is started to rotate the impeller. The delivery valve is kept closed in order to reduce valve is opened. The liquid is made to flow in an outward radial direction, thereby veins of impeller at the outer circumference with high velocity at outer circumference due to centrifugal action. Vacuum is created. This causes liquid from sump to rush through suction pipe to eye of impeller, thereby replacing long discharge from center circumference of the impeller is utilized in lifting liquid to required height through delivery pipe. Working operation of a centrifugal pump is explained in the following steps. Close the delivery valve and prime the pump. Start the motor connected to the pump shaft. This causes an increase in the impeller pressure. Open the delivery valve gradually, so that the liquid starts flowing into the deliver pipe. A partial vacuum is created at the eye of the centrifugal action. The liquid rushed from the sump to the pump due to pressure difference at the two ends of the suction pipe. As the impeller continues to run, move and more liquid is made available to the pump at its eye. Therefore, impeller increases the energy of the liquid and delivers it to the reservoir. While stopping the pump, the delivery valve should be closed first, otherwise there may be backflow from the reservoir. It may be noted that a uniform velocity of flow is maintained in the delivery pipe. This is due to the special design of the casing. As the flow proceeds from the tongue of the casing to the delivery pipe, the area of the casing increases. There is a corresponding change in the quantity of the liquid from the impeller. Thus, a uniform flow occurs in the delivery pipe. Operation difficulties in centrifugal pumps. Case 1: pump fails to pump the fluid. Causes. Remedial measures. Improper priming due to leakage of foot valve or incomplete filling. Repair or replace the foot valve, prime completely. Head more than design head. Reduce the head or change the pump. Clogging of impeller, suction pipe, or strainer. Clean the suspected part. Speed more than design speed. Connect another prime mover of higher speed. Direction of rotation of impeller is wrong. Change the direction. Suction lift may be excessive. Reduce the height of pump above the sump. Case 2: pump does not give the required capacity. Case 3: pump has poor efficiency. Causes. Remedial measures. Leakage of air through the suction pipe or through the gland packing. Stop the leakage. Damage to some parts of the pump by wear and tear. Replace the damaged parts. Clogging of impeller passages. Clean the impeller. Causes. Remedial measures. Higher than design speed. Reduce the speed. Low head and higher discharge. Reduce the discharge. Impeller touching, the casing or improper alignment of shaft. Carry out the necessary repair. Case for pump stop working causes. Remedial measures. Air entry into suction pipe. Stop the pump, plug the leakage, reprime, and start. Suction lift is high. Reduce the suction lift. Advantages of centrifugal pumps. The centrifugal pump's advantages include the following. These pumps do not include drive seals that reduce leakage risk. These pumps are used to pump out harmful and risky fluids. These pumps have magnetic coupling that can be damaged simply in overload situations as well as protects the pump from external forces. The motor and pump are separated from each other so heat transfer is impossible from the motor to pump. These pumps generate low friction. Disadvantages of centrifugal pumps. The centrifugal pump's disadvantages include the following. The energy loss can be occurred due to the coupling that generates some magnetic resistance. Once the intense load occurs, possibilities are there for the coupling fall. If fluids with ferrous particles are pumped out, then rust occurs and over the time pump stops working. When the flow of liquid is less through the pump, then the overheating can occur. Applications of centrifugal pumps. The centrifugal pump's applications include the following. Oil and energy pumping crude oil, slurry, mud, used by refineries, power generation plants. Industrial and fire protection industry heating and ventilation, boiler feed applications, air conditioning, pressure boosting, fire protection sprinkler systems. Waste management, agriculture and manufacturing wastewater processing plants, municipal industry, drainage, gas processing, irrigation, and flood protection. Pharmaceutical, chemical and food industries paints, hydrocarbons, petrochemical, cellulose, sugar refining, food and beverage production. Various industries, manufacturing, industrial, chemicals, pharmaceutical, food production, aerospace etc., for the purposes of cryogenics and refrigerants. Thank you for watching the video. Reciprocating pumps will be discussed in next video. For now, please subscribe, like, share and do not forget to press bell icon.